Deep learning is a branch of artificial intelligence that uses large neural networks to learn from data and perform complex tasks such as natural language processing, computer vision, and speech recognition. Deep learning models have achieved remarkable results in various domains, such as generating realistic images, writing coherent texts, and playing strategic games. However, these models also come with a significant environmental cost. They consume a massive amount of energy and generate a large amount of greenhouse gas emissions. The energy consumption and carbon footprint of deep learning models depend on several factors, such as the size of the model, the amount of data used for training and inference, the type and location of the hardware, and the source of electricity. According to a 2019 study by Struble et al., training a single deep learning model can generate up to 626,155 pounds of CO2 emissions, roughly equal to the total lifetime carbon footprint of 5 cars. As a point of comparison, the average American generates 36,156 pounds of CO2 emissions in a year. The trend in deep learning research is to build ever larger models with more parameters, more data, and more compute. For example, OpenAI's GPT-3 model, which was announced in June 2020, consists of a whopping 175 billion parameters and required several thousand petaflop days to train. This is orders of magnitude larger than its predecessor model GPT-2, which had only 1.5 billion parameters and took a few dozen petaflop days to train. The exact energy consumption and carbon footprint of GPT-3 are not publicly available, but they are likely to be much higher than those of GPT-2. The environmental impact of deep learning models is not limited to the training phase. The inference phase, which involves using the trained model to make predictions or generate outputs, also consumes energy and emits carbon. For example, using GPT-3 to write an email or a tweet requires sending a query to a server that hosts the model and receiving a response. This process involves data transmission over the Internet, which also has a carbon footprint. Moreover, some deep learning models are constantly updated with new data or retrained periodically, which adds to their energy consumption and carbon emissions. The main motivation for building larger deep learning models is to achieve better performance on various tasks and benchmarks. Larger models tend to have more expressive power and can capture more complex patterns and relationships in the data. However, this comes at the expense of efficiency. Larger models require more memory, storage, bandwidth, and computation resources. Moreover, larger models may suffer from diminishing returns or overfitting beyond a certain point. Adding more parameters or data may not improve the performance significantly or may even degrade it. Therefore, there is a trade-off between performance and efficiency in deep learning research. On one hand, researchers want to push the boundaries of what is possible with AI and explore new frontiers of knowledge and innovation. On the other hand, researchers need to consider the environmental and social implications of their work and seek ways to reduce the energy consumption and carbon footprint of their models. This trade-off poses ethical and practical challenges for the AI community. There are several possible solutions for reducing the carbon impact of deep learning models without compromising their performance. Some of these solutions include: 1. Using more efficient hardware and software. Developing and using hardware and software that can run deep learning models faster and with less power consumption can help reduce the energy consumption and carbon footprint of these models. For example, Using specialized chips such as GPUs or TPUs instead of CPUs can speed up the computation and lower the energy cost. Similarly, using optimized algorithms or frameworks that can reduce the redundancy or complexity of the models can also improve their efficiency. 2. Using renewable energy sources. Switching to renewable energy sources such as solar or wind power can help reduce the carbon emissions associated with running deep learning models. For example, Google claims that its data centers are powered by 100% renewable energy. However, this solution may not be feasible or accessible for all researchers or organizations due to geographical or economic constraints. 3. Using smaller or simpler models. Reducing the size or complexity of deep learning models can help reduce their energy consumption and carbon footprint. For example, using techniques such as pruning, quantization, distillation, or sparsification can help compress or simplify the models without losing much performance. Similarly, using techniques such as transfer learning, meta-learning, or few-shot learning can help leverage existing models or data and reduce the need for training new models from scratch. 4. Using carbon offsetting or removal. Compensating for the carbon emissions generated by deep learning models by investing in projects or initiatives that can reduce or remove carbon from the atmosphere can help mitigate the environmental impact of these models. For example, buying carbon credits, or certificates that represent a reduction or removal of 1 ton of CO2 can help offset the carbon footprint of a deep learning model. However, this solution may not be sufficient or sustainable in the long term, as it does not address the root cause of the problem. While deep learning models can contribute to the climate crisis, they can also play a vital role in solving it. AI can be used to enhance and accelerate efforts across various domains related to climate change, such as climate research and modeling, climate finance, renewable energy, smart transportation, agriculture, and education. According to a 2020 report by BCG and Microsoft, AI can help reduce global greenhouse gas emissions by up to 4% in 2030. Which is equivalent to 2.4 gigatons of CO2. Moreover, AI can help generate up to $5.2 trillion of additional global GDP in 2030, by enabling growth and innovation in low-carbon sectors. Therefore, AI can be a powerful ally in the fight against climate change, if used responsibly and ethically. The AI community needs to balance the trade-off between performance and efficiency and adopt best practices and standards for measuring and reducing the carbon impact of deep learning models. The AI community also needs to collaborate with other stakeholders, such as policymakers, regulators, investors, consumers, and civil society, to ensure that AI is aligned with the goals and values of humanity and the planet.